All right, let's talk about one of the biggest updates to the Go language, generics. This is a feature that really changes the game when it comes to writing flexible, reusable code, all while keeping that rock-solid type safety that we all love about Go. So let me ask you this. Have you ever been in that situation where you write a function, it works perfectly, and then you realize you need the exact same logic for a different type? Like for a float instead of an int. You end up just copying and pasting the whole thing? It's frustrating, right? Well, that exact problem is the perfect jumping off point for what we're talking about today. Okay, so first let's get really specific and look at this problem up close. We're going to examine a classic example of code duplication, the exact kind of thing that generics are designed to make disappear. Take a look at these two functions on the screen. On the left, we've got some ints, and on the right, some floats. One adds up integer values from a map, the other adds up float values. But if you really look at them, the logic inside is absolutely identical. The only thing that changes is the type. int64 here and float64 over there. And this, right here, is the core of the problem. It kind of goes against a huge principle in programming, don't repeat yourself, or DRY. I mean, having two functions to maintain is just not efficient. If you find a bug in one, you have to remember to fix it in the other. It's a total headache, and it's exactly what generics are here to solve. And that brings us to the really cool part, the solution. We're going to take that duplicated code and refactor it into one single, way more powerful, generic function. Okay, check this out. This is our new generic function, sum int or floats. Now I know there's some new syntax here. That part in the square brackets, that is where all the magic is happening. It's where we're telling Go that this function isn't tied to one specific type, but will work with some placeholder types instead. So those letters you see, the K and V, those are what we call type parameters. The easiest way to think about them is like variables, but for types. They're just placeholders. K is going to stand in for our map's key type, and V will be for its value type. Later, when we actually call the function, we'll tell Go what real types to plug in there. But we can't just plug any type in there. We need some rules, and those rules are called type constraints. So for our key, K, the constraint is comparable. That's built into Go, and it just means the type has to support being compared with equals equals or not equals, which, is a requirement for any map key. For our value, V, the constraint is int64/float64. That vertical bar, the pipe, just means or. So V can be an int64 or a float64. That's it, nothing else. And here's how we actually use it. It's pretty cool. When we call the function, we pass what are called type arguments inside those square brackets. So in the first call, we're explicitly telling Go, hey, for this run, K is a string and V is an int64. In the second one, K is a string and V is a float64. And look at that. One function handles both types and gives us the correct sum for each. It's so clean. But wait, it gets even better. Because Go is a pretty smart language, it can often make our code even cleaner with the feature called type inference. Just look at the difference here. On the left is that call we just saw where we spell everything out, but on the right, notice we've completely left out the square brackets and the types. So how does that work? Well, the Go compiler is smart enough to just look at the ints map that we passed in, and it infers that the keys must be strings and the values must be int64s. It just figures it out for us. And this is a huge win for readability. Most of the time, you're not even going to have to write out the types. The compiler does the heavy lifting, which gives you code that is way cleaner and easier to read, and you don't lose any of that critical type safety. We can actually take this one last step to make our code even more elegant. What if we made our constraints reusable? This is a fantastic trick for keeping your code super organized. So instead of writing int64/float64 right inside our function signature, we can define a new constraint and give it a name, like number. Here, we're using an interface to say that any type that wants to be a number has to be either an int64 or a float64. And now, look how much cleaner our function signature is. We've even renamed it to some numbers. The constraint for V is just number. This is so much more descriptive. It clearly says what the function does. It sums a map of numbers. And think about this. If we ever wanted to add int32 to the list of numbers we can sum, we would only have to change the number interface in one place, and this function would just automatically support it. That's powerful. Okay, so let's zoom out and look at the big picture. Why is this feature such a massive deal for everyone who writes Go? It really boils down to three key things. First, we can write way more abstract and reusable code, just like that sum numbers function we ended up with. Second, and this is crucial, we do all this without giving up an ounce of Go's static type safety. The compiler is still there to protect us. And third, we get to delete all that duplicated code we started with, which makes our project so much easier to build and maintain. So we've gone on a quick journey here, right? We started with a clunky, repetitive pair of functions, and we ended with a single, elegant, type-safe, and reusable solution. The question I want to leave you with is this. Now that you have this powerful tool in your toolbox, how is this going to change the way you build things with Go?